Good evening, everyone. We are going to start our week 8 session. In the week 8 session, we are discussing the problems related to week 7 and week 6. Okay, so first problem, it's related to the TIG. So the question is, during a TIG welding process, the arc current and arc voltage were 50 ampere and 60 volt respectively. When the welding speed was 150 millimeter per minute. In another process, the TIG welding carried out of the welding speed of 120 millimeter per minute at the same arc voltage and heat input to the material, so that weld quality remained the same. The welding current for this process. So you have to calculate the current value. So what are the input is given? Total heat you have to first calculate. For that, total heat you can write it as VIT. Okay, so V will be the voltage here, that you can write it as I square RT also in joules, that is watt second. Okay, and here V is the arc voltage and I is the arc current. Now R is the resistance of the material and T is time in seconds. So what we have to do, we have to calculate the heat input per unit length. So it will be Q, that we can write it as VI divided by small letter v, that is the velocity, means welding speed. Okay, now the given values we can write it as, it is I is given, that is 50 ampere I1, and V1 is equal to VT is equal to 60 volt, which is given, and small letter V1 first velocity millimeter per minute, and similarly V2 is 120 millimeter per minute. Now, and we have know that Q1 is equal to Q2. Then you have to submit V1 I1 divided by V2 is equal to V2 I2 divided by V2. From there, you have to calculate I2 divided by 120, that is equal to 50 divided by 150. From there, you will get the value of I2, that will be 40 ampere. That will be the welding current for the process. So how in this case I'm repeating the question once again. During a TIG welding process, the arc current and arc the arc current and arc voltage were 50 ampere and 60 volt respectively when the welding speed was 150 millimeter per minute. In other process, the TIG welding is carried out of a welding speed of 120 millimeter per minute at the same arc voltage and heat input to the material. So the welding quality remained the same. The weld current for this process. So you have to calculate the weld current. What are the things are given? Welding speed of two cases is given, and the voltage is arc voltage is same to the system, and heat input of the material also same. So now you have to only think about the heat rate, heat input per unit length. You have to calculate, that is equal, that is given in the question. So you equate the heat input per length, both if you get, and you have to find the value of I2 from that. So you will get the value of I2 after solving this 40 ampere. Thus you go through this problem and we will go to the next one. Now we will go to the second problem. The problem is for the same value of peak pressure, peak temperature and heat rejection, the current order of the efficiencies for Otto, dual and diesel cycles is. So here you have to know about the Otto cycle, dual cycle and diesel cycle and how the efficiency will be. Which means the conditions are given, it should be same peak pressure, peak temperature and heat rejection. So what will be the answer for this? So in this case, the correct answer one, this one. Diesel will have more efficiency than dual cycle than Otto cycle. For some compression ratio, means if you have, this is like peak pressure and peak temperature and heat rejection ratio is given. Isn't it same compression ratio if come? Same compression ratio and heat rejection or So if it is same compression ratio and heat addition, then option 1 will be the correct answer. So here in this question answer option 3 is the correct one, which means same values of peak pressure and temperature and diesel cycle is more efficient and Otto cycle is least efficient. Okay. But if you consider same compression ratio and heat addition, then it answer will be option 1. Now, if we go to the next question, a cylindrical uranium fuel rod of radius 5 mm in a nuclear reactor is generating heat at the rate of 4 times 10 to the power 7 watt per meter cube, and the rod is cooled by a liquid. Transfer coefficient is 1000 watt per meter square Kelvin at 25 degrees Celsius. At steady state, the surface temperature of the rod is. So you have to calculate the surface temperature of the rod. So how to do that? For a So for a cylinder, the temperature TW, you can write it as T alpha plus Q R divided by 2H. Similarly, Tc you can write it as Tw plus Q R square divided by 4K. Okay, here Tw is the wall or surface temperature in Kelvin. And Tc is the center temperature. And T infinity you can tell the temperature of surrounding. Okay, that's also in Kelvin. And Q means it is the heat generated. That will be watt per meter cube. And H is the heat transfer coefficient. So H will be and R is the radius of the cylinder. From this you have to calculate the surface temperature of the rod in Kelvin. So for that we first will write what are the input parameters. So R will be 5 millimeter, which is given. The heat generated, that is given 4 times 10 to the power 7 watt per meter cube. And T infinity, surrounding temperature, which is given. That is 25 degrees Celsius, that you can write it as 298 Kelvin. Similarly, H value is given 1000 watt per meter square Kelvin. Now you have to calculate the surrounding temperature TW, that will be TR infinity, which means surrounding temperature is divided time plus Q times 2HR. So you can give the values here. 298 plus Q value is given 4 into 10 to the power 7 divided by 2 times 1000 times radius is given millimeter. You have to convert it into meter. It will be 10 to the power minus 3. Then here you have to find the value of the temperature TW, that is surface temperature of the system. Everyone try this and please inform how much is the answer you are getting. Substitute this value in the formula and let me know. Yeah, answer is 398. So if we substitute here, we will get the answer 398 Kelvin. So the surface temperature will be 398. Okay, now we will move to the next question. It's a very important question. In a double pipe counterflow heat exchanger, 10,000 kilogram per hour of an oil having specific heat of 2095 joule per kilogram Kelvin is cooled from 80 degrees Celsius to 50 degrees Celsius by 8,000 kilogram per hour of water entering at 25 degrees Celsius. Determine heat exchange area required if overall HT coefficient, heat transfer coefficient will be 300 watt per meter square Kelvin. Okay, so take CP value of water also given, that is 4180 joule per kilogram Kelvin. So here first we will draw the diagram first. So you have to, if you consider a heat pump, okay, so oil is flowing in the pump and we are filling it with a cold water. So water is entering here. So it's moving out from this opening. Okay, so here what that hot temperature, hot liquid, that is oil in this case, and the cold liquid is water. So in so TCI, which is given, that is 25 degrees Celsius, that is the cold temperature, and THO is given 50 degrees Celsius, and T in HI. So heat liquid input is 80 degrees Celsius. After coming out of the heat exchanger, it is become 50 degrees Celsius, and cold water. So we have to find the TCO. How much is the water temperature after using from this heat exchanger. So that we have to find first, then you have to calculate the determine the heat exchanger area required. So in this situation, first the mass rate. So mass rate you can that you can write it as 10,000 kilogram per hour. Similarly, CH value is given, that is 2095. Similarly, mass rate of the cold liquid also given 8000 kilogram per hour. Cc value is also given 4180 joule per kilogram. Okay, now you have to calculate the Q value. Q value, how you can write mass rate? MHCH times THI minus THO. That is similar as this is the amount of heat lost by the heat fluid, and that will be same as the amount of heat gained by the cooled fluid also. So you can write it as MC dot Cc times TCO minus TCI, and this will be equal to the value U a potential energy and A is the area and the value of LMTD. Now from this, what you have to calculate, if you see here, you know the value of all the parameter other than TCO. So you have to, from that, you have to calculate the value of TCO. TCO, you will get it 43.8 degrees Celsius. So from this problem, from these two equation, you got the value of TCO. It will be 43.8 degrees Celsius. And now, if we draw the temperature distribution as normal, how we are drawing same way. So THI, that is 80 degrees Celsius, which is given, and it's coming down, that is THO will be 50 degrees Celsius. Okay, similarly TCO is given 43 degrees Celsius, and it will be then TCI, input will be 25 degrees Celsius and output will be, the temperature should be I, that is 43 degrees Celsius. Now from here, what you have to calculate, you have to first calculate to solve this one. Q is equal to UA LMTD. So first you have to calculate the LMTD value. For calculating LMTD, you have to calculate the delta T, that will be THI minus TCO. Similarly, if you do this, you will get answer here 36.2, and here it will be delta T2, you can write it as THO minus TCI, it will be 25 degrees Celsius. Now what you have to do, you have to calculate the LMTD value. LMTD value will be delta T1 minus delta T2 divided by log delta T1 divided by delta T2. So substitute these values. So here it will be 36.2, and this one will be 25, and substitute these values and find the LMTD value. So how much will be the LMTD values here in degrees Celsius? So your LMTD value, how you will get it? 30.26 degrees Celsius. So that will be the LMTD. Now what you have to do, you have to calculate the Q value. So Q is equal to MHCH times THI minus THO. From this, every values are given. So 10,000 divided by 3 times 2095 times 30. So this will be the Q value, total heat. So how much will be the total heat after calculating this? It is a big value, 174583.33 watt. From this, you have to find the value of area. So area, you can write it as Q divided by U times LMTD. Substitute the value. Q will be the value given here, and U value will be 300, and LMTD you already calculated, that is 30.26. So find the value of area. How much will be the area in meters square? Please calculate it. How much is the value you got it for area? It will be 19.23 meters square. So in this problem, we first have to know about the uh, TCO value, means output water temperature, and from there you have to calculate the Q value. First for calculating, you have to calculate LMTD that we discussed already in the earlier classes. After that LMTD value, from that you have to calculate Q value, total heat in the system, and from there the area of the heat exchanger. Now, if we go to the next problem will be a thermoelectric power of iron and copper with respect to lead are plus 10.5 and minus 3.5 microvolt respectively at 100 degrees Celsius. So, find the EMF of CuFe thermocouple when its junction are maintained at 50 degrees Celsius and 150 degrees Celsius. So, here what are the values are given? The thermoelectric power is given, that we can write it as S. So SPB Fe is given, that is 10.5 microvolt. Similarly, SPB Cu is given minus 3.5 microvolt. Okay, so according to law of intermediate metal, like you can write it as, you have to find here Cu and Fe. So for that, S of CuPb plus S of Pb Fe. So that you can write it as minus of S of PbCu, that is given, plus FPb Fe. So it will be minus and minus plus. So 3.5 plus 10.5 you will get it. So from that the answer will be 14 microvolt. So the S value is we got 14 microvolt. Find the EMF. So EMF you have to find. For finding EMF, it will be the delta T. So you can write it as EMF is equal to 14, that is the power rate, this one, times 100. So it will be 1400 microwatt, that you can write it as. So EMF with respect to copper and iron, it will be 1400 microwatt. Now, if we move to the next problem is very important. It's also related to the heat exchanger. So, a concentric counter current heat exchanger is used to cool lubricant oil. Water is as a coolant. The inlet and outlet temperature as given in the table. The mass flow rate of the oil into the heat exchanger is 0.1 kilogram per second. What is the mass flow rate of the water needed to maintain these operating conditions? Okay. So if you see the heat exchanger here, you can clearly see that this will be the heated part, the red color one, and the heat is reducing, it coming out. So here water is entering here, means coolant is entering here, and coolant is getting more heated to in this direction. And okay, the oil is amount is here. Now mass flow rate of oil is given, mass flow rate of water you have to calculate. So the inlet temperature and outlet temperatures are given for both liquids. Now what we have to do, we have to find the mass rate of the water needed to maintain the operating conditions. Okay. Now So for that, which formula we have to use? So we know that Q, heat rate, will be mass rate times Cp delta T. Okay, so here you can clearly write it as that a mass rate of oil and Cp of oil will be T inlet of oil minus T outlet of oil. That will be same as the water case. So mass rate of water and Cpw, similarly C out W minus C in W. So that Cp oil, which is given that 2131 joule per kilogram degree Celsius. Similarly, Cp water will be 4178 joule per kilogram degree Celsius. Now equate this formula, equate this, and you have to find the value of mass rate of water. So how about it will be mass rate of oil, Cp of oil times T inlet of oil minus T outlet of oil divided by this one, Cp W times T outlet of W minus T in of W. So substitute the value. So here it will be 0.1 times 2131 times 45 degrees Celsius divided by 4178 times 7. So you have to calculate this value, then find the answer for the mass rate. So how much you are getting the value here? It will be 0.33 kilogram per second. So now we'll go to some theory questions. So first one is heat pipe transport heat dominantly in. So heat pipe transport will be in one dimension, two dimension, three dimension, or all of the above. So in the heat pipe, the transport heat dominantly in the one dimension. So the answer will be one dimension. Now, if you see here, a thermoelectric generation, that is TEG, is associated with the following characteristics. First one is it is directly convert electrical energy to the thermal energy within higher efficiency, and it requires cesium or cadmium doped semiconductor for its operation, and C, multiple metal blocks with similar temperature gradient across its oppositely positioned surface can be connected in series through wires to obtain the higher EMF, and option D is none of the above. So if it is a thermoelectric generation, so thermoelectric generation means it's converting thermal energy to electrical energy. So the first option is wrong here. The correct answer for this none of the above. So none of the above is not the correct answer. So and if you go for the next question, the figure of merits of TEG is a function of dash and the increase if dash. So in this question, the figure of merit of TEG system depends on what? Electrical property or resistance of the applied load. Similarly, material properties and geometry, and material properties plus resistance of the applied load, and material properties and temperature difference. So similarly, you have to say that the figure of merit will increase when the electrical conductivity increases, otherwise increasing the thermatical. Electrical conductivity increase and thermal conductivity decreases, and electrical conductivity decreases and thermal conductivity increases, and conductivity increase, thermal conductivity decrease, and temperature difference. So actually there are three factors which is depend on the figure of merit of the TEG system. One is conductivity, electrical conductivity, another one is thermal conductivity, then temperature difference. So the answer will be answer B. So the material property and geometry depends on the figure of merit, and it will increase if the electrical conductivity increase and the thermal conductivity decrease the system. The next question, which is the material used as seed particle in the MHD generator system and what does it do? So the materials options are given. The rubidium produces more charged particles. Cesium helps to attain ionization potential at low temperature. Potassium increases the working range of the temperature of an MHD generator, and beryllium increases the velocity of the gas. So the answer will be cesium, which helps the ionization potential at the lower temperature to help to attain the ionization potential. So next question is little bit lengthy question, but it is very important question also. So we want to recover waste heat from the exhaust gas as of a car using thermoelectric generator, that is TEG modules as shown in the figure, which is figure is given here. An array of n is equal to 24 TEG module is installed in the exhaust of the car. Each module has n is equal to 98 thermocouples, each which consist of p-type and n-type thermoelements. Now, exhaust gas flow through the TEG device, wherein one side of the module experience the exhaust gas, while other side of the module experience the coolant flows. Now, these cause the hot and cold junction temperature of the module to be 230 degrees Celsius and the 50 degrees Celsius respectively. To maintain the junction temperature, the significant amount of heat should be absorbed at the hot junction and liberated at the cold junction, which is usually achieved by the heat sinks. The material properties of the p-type n-type thermo elements is assumed to be alpha p, that is equal to alpha n is equal to 168 microvolt per Kelvin, and the alpha is the seeback coefficient, and the resistivity rho P and rho N will be same as, it will be 1.56 times 10 to the power 3 ohm centimeter, and the thermal conductivity K value is given, that is 1.18 times 10 to the power minus 2 watt per centimeter Kelvin. The cross-sectional area and the leg length of the thermo element is given, that is 12 millimeter square, and L and LP value will be 4.6 millimeter. Now, what you have to calculate per 1 TEG module, compute the electric current, the voltage, and maximum power output and maximum power efficiency. Similarly, you have to calculate for the whole TEG values, compute the same values: maximum power output, maximum power efficiency, and maximum conversion efficiency, and the total heat absorbed at the hot junction. So these many things you have to calculate. So for first, if you consider the figure of merit said, you can write it as alpha square divided by rho k. So all values are given. So 336 times 10 to the power minus 6 whole square divided by 3.12 times 10 to the power minus 5 and 2.36. So the answer will be 1.533 times 10 to the power minus 3 Kelvin inverse. So this will be the figure of merit, and you can write set T cap is equal to set times Tc plus Th divided by 2, the average values of temperature. That you can write it as, substitute the values, then 1.533 times 10 to the power minus 3 that we got from the earlier problem, then it will be 323 plus 503 divided by 2, the answer will be 0.633. Okay, now if you for the maximum power output, you can for maximum power output, RL divided by R, which should be 1. So the internal resistance R, how much it is, rho L divided by A, that is non formula for all of us. So it will be 3.12 times 10 to the power minus 5 times 4.6 times 10 to the power minus 3 divided by 12 times 10 to the power minus 6 meter square. So it will be 0.012 ohm. So ohm value we got it. Now for 1 TEG, 1 TEG, you can write it as alpha TH minus TC divided by RL plus R. So R value is already we found, RL value is also same, and what is alpha value is also given, and TH and TC is also given. So how much it will be, you can write it as 336 times 10 to the power minus 6 in the 230 plus 273 Kelvin minus 50 plus 273 Kelvin divided by 0.012 ohm plus 0.012 ohm. So the answer will be 2.528 ampere. Okay, so that will be the current. Now you have to calculate the total voltage. It will be N alpha times TH minus TC divided by RL divided by R plus 1, so times RL divided by R. So substitute these values, you will get 98 times alpha values already we found, that is 336 times 10 to the power minus 6. Then again you have to calculate the temperatures, Th minus Tc divided by 1 plus 1, it will be 292.964 watt. Now we have to calculate the maximum power output, that will be n alpha square th minus tc whole square divided by r times RL divided by capital R by 1 plus RL divided by R whole square. Substitute the values and let me know what is the answer we are getting. So here you will get the power output will be 7.493 watt. Okay. Now we have to calculate maximum power efficiency, that you can calculate eta mp is equal to 1 minus tc divided by th divided minus 2 minus half times 1 minus tc divided by th plus 2 divided by zt bar times 1 plus tc divided by th. So substitute all the values. Tc value already know, th already know, and we found the zt values also. Substitute here and find the maximum power efficiency for one TEG module. So after substituting all values, you will get the answer is 0.051. That will be the efficiency. Now if you see this problem is little bit lengthy, but method is very simple. You have to calculate the TEG module, one TEG module, electric current, voltage and maximum power output and maximum power efficiency. Then you have to count it for the whole TEG. So one TEG and then total number of range is 24. So you have to multiply this power values to by 24. That is a B session that you have to do in the for the next class. So for this case, for the first question, what will happen, like first you have to find the set value alpha squared by rho k. Alpha is values are given, so you have to just substitute, find the value, series value, and then V T bar average temperature it will be, and we have to calculate from there. For one TEG, first you have to calculate the current, then voltage, then power, then efficiency, total power efficiency also you have to calculate using these formulas. And the B question you people try for the next class. The question is the whole TEG device to compute the maximum power output and power minimum, maximum power efficiency and maximum conversion efficiency, and the total heat absorbed to the hot junction. Though we have to calculate for one TEG we calculated. Now we have to calculate it for the 24 TEG. What will be the power output and power efficiency? Okay. So now we are winding up here. So you just solve this B question for the next class. We will discuss the answer for this next class.